Okay, welcome back all of you. In the last lecture, we have seen the importance of pore water pressure in soils and the need for its estimation. We discussed about Skempton's pore water pressure equations and A and B parameters, which are known as Skempton's pore pressure parameters. So, this lecture is continuation of the last lecture, and we will basically deal with pore water pressure for plane strain conditions, Henkel's pore water pressure equation, and the effect of sampling on pore water pressure which occurs in the field. So, these three aspects we will cover in today's lecture. So, for specific geotechnical problems, we have already seen plane strain condition is more realistic than triaxial condition. We have already seen this. So, we will try to have the derivation for delta U corresponding to plane strain. Now, the condition for plane strain, let us say we have, if you deal with principal stresses and principal strains, let us consider intermediate principal strain epsilon 2 is equal to 0, and that can be expressed as sigma 2 dash by E minus mu by E sigma 1 dash plus sigma 3 dash. This gives sigma 2 dash by E is equal to mu by E sigma 1 dash plus sigma 3 dash. In terms of incremental stresses, we can write delta sigma 2 dash is equal to mu into delta sigma 1 dash plus delta sigma 3 dash. Now, how did we derive the pore water pressure equation? We have associated, or we have already allocated, we saying that there will be some volume change that can occur in undrained condition. Then we associated this volume change to the compressibility of water. Then we have derived the equation for pore water pressure. Doing the same thing for plane strain. So, we will have to start from the same point. Whatever is the volume change, that is due to compressibility of water. Doing that, associating the volume change under undrained condition to compressibility of pore water, we can write this is the starting point, NCW delta U equal to 1 minus 2 mu by E delta sigma 1 dash plus delta sigma 2 dash plus delta sigma 3 dash, associating the undrained volume change that could have happened due to delta U to the actual volume change that would have happened under drained condition. Then delta sigma 2 dash can be replaced by this equation. So, when you replace that, you get this equation. So, rearranging the terms, you get NCW delta U equal to 1 minus 2 mu by E 1 plus mu delta sigma dash plus 1 plus mu delta sigma 3 dash. So, 1 plus mu can be taken outside. This gives 1 plus mu 1 minus 2 mu by E delta sigma 1 dash plus delta sigma 3 dash. Again, we can make some mathematical rearrangement like the way we have done it. So, we plus and minus delta sigma 3 dash into the equation. So, that will give 2 delta sigma 3 dash plus delta sigma 1 dash minus delta sigma 3 dash. Now, this equation is similar to the equation that we have seen during the derivation of Skempton's pore water pressure equation. So, this has become very similar to that. Now, if we take 2 outside from this, 2 into 1 plus mu 1 minus 2 mu by E is equal to delta sigma 3, and we are expressing this effective stress in total stress. So, delta sigma 3, the 2 has gone outside, plus half into delta sigma 1 minus delta sigma 3 minus delta U, because delta U comes from here. Now, if we take this delta U on the other side, So, all these things 2 1 plus mu 1 minus 2 mu by E delta u goes on the other end. So, you will get this NCW plus 2 into 1 plus mu 1 minus 2 mu by E into delta u is equal to 2 into 1 plus mu 1 minus 2 mu by E into delta sigma 3 plus half delta sigma 1 minus delta sigma 3. Now, if you notice, this is now very much similar to the Henkel's Pore water pressure equation, except the fact that there it was 1 by 3 and now it is half. Again rearranging, delta u is equal to 2 into 1 plus mu 1 minus 2 mu by E upon NCW into 2 into 1 plus mu 1 minus 2 mu by E, and this bracket remains the same. Again rearranging, you can get 1 by 1 plus E NCW by 2 into 1 plus mu 1 minus 2 mu. So, the final Pore water pressure equation will be delta u is equal to 1 by 1 plus N Cw by Cs. This is the same way we have done compressibility of soil skeleton, the same thing we have done before also, and E comes down. So, Cs is the compressibility of soil skeleton for specifically for plane strain condition, and that is equal to 2 into 1 plus mu 1 minus 2 mu upon E. So, what is the essential difference between plane strain and triaxial condition? So, A parameter for triaxial condition is 1 by 3, whereas for plane strain condition A is equal to half. Remember, this values 1 by 3 and 1 by 2 corresponds to elastic behavior only. So, that is about the derivation of equation for plane strain condition. Now, let us see Henkel's pore pressure equation in terms of octahedral stresses. Henkel 1960 proposed new equation for delta u in terms of octahedral stresses. I hope you remember what is octahedral stresses, which we have seen in the earlier lecture. So, according to Henkel, it is delta u is equal to beta sigma octahedral plus 3 alpha delta of tau octahedral. So, both sigma octahedral and tau octahedral has been accounted. This is very much similar to our previous Henkel's equation. B is replaced by beta, A is replaced by 3 into alpha, because tau octahedral mostly it represents condition similar to that of deviatoric stress, which is sigma 1 minus sigma 3 for triaxial condition. So, it is one and the same. Now, sigma octahedral, just to revise, let us write sigma octahedral is equal to mean principal stresses or mean stress P. I am not intentionally putting prime, because now it corresponds to total stress condition, because pore water pressure is there, it is an undrained condition. So, I am referring it to P, mean stress. And tau octahedral, the relationship with the deviatoric stress is root 2 by 3 into Q. All these expressions we have seen in the previous lectures. Now, if you rearrange in terms of P and Q, one can write beta is equal to delta P plus alpha into root 2 into delta Q. So, we are just replacing it in terms of P and Q. Here alpha and beta are called pore water pressure parameters, just like A and B. And here also beta equal to 1 for fully saturated sample. So, this is about Henkel's pore water pressure equation. We need to understand that this equation is in terms of octahedral stresses. So, in those models which adopt octahedral stresses, it is quite handy to see how the pore water pressure changes with corresponding changes in the octahedral stresses. Now, let us try to find out the relationship between alpha and A, because these two parameters are similar. One is in Henkel, the other one is in Henkel's pore pressure equation. For constant confining pressure, so there are conditions given for constant confining pressure during compression of a saturated clay. So, there are certain things which comes out from here, that is there is no change in confining pressure, that is constant confining pressure. So, delta sigma 2 equal to delta sigma 3 equal to 0. Since it is saturated, beta is equal to 1 and B is also equal to 1. So, let us first start with Henkel'S pore pressure equation. So, this is Henkel's pore water pressure equation. So, here we know that delta sigma 2 equal to delta sigma 3 equal to 0. Substituting that, we will get delta u is equal to A into delta sigma 1. Now, this is the Henkel's pore pressure equation which we have just seen. We know sigma octahedral is equal to delta P, which is equal to delta sigma 1 plus 2 delta sigma 3 by 3. So, delta sigma 3 is 0, that gives delta sigma 1 by 3, and tau octahedral is root 2 by 3 delta Q. Now, for corresponding to a typical triaxial condition, we know that Q is equal to sigma 1 minus sigma 3. So, delta Q is equal to delta sigma 1 minus delta sigma 3 root 2 by 3, which is equal to root 2 by 3 delta sigma 1. So, we will substitute this back into the equation. So, this will give delta sigma 1 by 3 plus root 2 alpha delta sigma 1. Now, for delta u, we already know this is equal to A delta sigma 1. So, substituting that here, A delta sigma 1 is equal to delta sigma 1 by 3 plus root 2 alpha delta sigma 1. Now, you will take this delta sigma 1 on the other side. So, that will give us A minus 1 by 3 into delta sigma 1 is equal to root 2 alpha delta sigma 1. So, delta sigma 1 gets cancelled off. So, we are left with A minus 1 by 3 equal to root 2 alpha. So, this gives the relationship between alpha and A, where after rearranging you can get alpha is equal to 3A minus 1 by 3 root 2. So, this is the relationship between alpha and A, but for specific condition where the confining pressure remains constant and the soil is fully saturated. So, this is about Henkel's pore water pressure equation and its relationship with Henkel's pore pressure parameter A. So, next let us see the effect of sampling in the field on pore water pressure. Many a times we need to sample soils from the field, specifically undisturbed soil sample, and this is very much important for studying the compressibility of the soil as well as the shear strength characteristics. If you want to plan a foundation at a particular level, we need to know what is the bearing capacity of that particular soil. So, we need to have the undisturbed sample with us. Now, during sampling, what happens? Let us say it is a saturated soil mass, and when you do the sampling, whether there is any change that can happen to the soil mass in terms of its pore water pressure. So, that is what we will see just now, and this part of the lecture I have taken from HEAD, Manual of Soil Laboratory Testing, volume 3, Effective Stress Tests, published by John Wiley. Let us consider a soil element A in the field. This is the depiction of a given soil. You can see that the ground surface is here, the water table is here, and we know this soil beneath the water table, it is saturated. So, accordingly the unit weight here will be bulk unit weight or total unit weight, and here it will be saturated unit weight. So, here please remember, this is not a saturated soil mass, it is a partially saturated. So, we will consider this to be bulk unit weight, and here it is saturated unit weight. We will consider a soil element A, which is shown here. Now, if you put a piezometer, what we will get? We will get the head causing what is the head of water. Now, here in this case it is a static pore water pressure or static head. So, here the water will rise in the piezometer up to the groundwater table. It is an unconfined case. We have vertical stress and horizontal stress acting. the thickness considered is Z and the thickness of the partially saturated portion, that is thickness above the water table, is H. So, here it is Z minus H. Okay. So, I am showing the kind of stresses which is acting here, which is sigma 1, sigma 2 and sigma 3. Soil is saturated and it is in equilibrium. Okay. So, this given soil, it is in saturated state and it is also in equilibrium. Please note that we are considering the element A. So, with respect to that, the soil is saturated. It is in equilibrium means what? The pore water pressure has reached to its equilibrium values, that is what it means. So, here we have static pore water pressure and that is denoted by U, static pore water pressure U. Let us see the total stress sigma 1, it is equal to sigma V. So, we are considering the vertical stress to be major principal stress, and sigma 2 is equal to sigma 3 is equal to sigma H. Now, sigma V, what will be sigma V from this figure? It will be gamma into H. So, this portion gamma into H plus whatever is the weight on top of it, which is equal to gamma sat into Z minus H. For example, if it is here, let us say that Z minus H is marked here. So, here sigma V is like almost you are considering the soil element here. So, it is one and the same because Z keeps changing depending upon where it is. So, please note that this Z minus H is up to this particular soil element. So, it is denoted in general. To be very specific, it will be here. Whatever has been marked here is in general. Okay. So, sigma V is equal to gamma into H plus gamma sat Z minus H, and initial pore water pressure UI is equal to Z minus H into gamma W. Again the consideration is with respect to here. Okay. So, if you consider Z minus H as this, that is equal to Z minus H into gamma W. So, that is the initial pore water pressure which is existing in the soil sample before sampling. So, one can write sigma dash V is equal to sigma V minus UI. So, that will give sigma V dash is equal to gamma into H plus gamma dash Z minus H, and sigma dash H is equal to K naught into sigma V dash. Okay. So, now the what is K naught? K naught is coefficient of lateral earth pressure at rest. So, sigma H can be written as sigma dash H plus UI. Now, why did we write this? Why can we write sigma H is equal to K naught into sigma V? Why can we write that? This is not possible because all these coefficient of lateral earth pressure, active passive case, all of them are in terms of failure condition, and hence it is not only failure condition, the lateral earth pressure is always in terms of effective stress. Why? Because we are considering the effect of soil or the lateral pressure of soil acting on something, and this is mostly dictated by the effective stress condition. So, the equation sigma H equal to K naught into sigma V in terms of total stress is not actually valid. It is always in terms of effective stress. That is why we have first found out what is the total vertical stress acting, then found out its effective component, then applied K naught for getting sigma H dash. Now, if you want to obtain sigma H, then we just need to add pore water pressure to it. So, that is what has been done here, which is sigma dash H plus UI, and that gives K naught into sigma dash V plus Ui. Now, let us consider the soil sample is taken from the field, that is the process of sampling. When soil element is sampled from the subsurface, the confining stresses are relieved. So, confinement now reduced to 0, that is true. So, when you are trying to when you try to take this particular soil maybe in a borehole, what we are doing is we are making a hole here. So, this is relieved, and when you take out the sample, this is also relieved. So, change in stress conditions induce change in pore water pressure. Now, just because there is a release of stresses or if the stresses are relieved, we will have changes in pore water pressure because it is under undrained condition, and it is for a smaller period of time. So, both combined, there will be changes in pore water pressure. So, let us start with the Skempton's pore water pressure equation. Delta U is equal, and then we need to find out what is the changes in delta sigma 3 and delta sigma 1. So, soil is a saturated mass. So, B can be considered equal to 1. Now, delta sigma 3 is what? The change in confining stress, sigma 3 final minus sigma 3 initial. Now, sigma 3 final, we know it is 0 because the confinement is lost, and sigma 3 initial is nothing but the lateral pressure, sigma h. So, this will give delta sigma 3 is equal to minus sigma h. Now, what is delta sigma 1? It is sigma 1 f minus sigma 1 I. Again, sigma 1 f is also 0 because it is sampled, minus sigma v, which is the initial major principal stress, that will give minus sigma v. If we substitute this in the equation, we will get delta u is equal to minus sigma h plus a into minus sigma v, minus of minus will become plus sigma h. So, delta u is equal to minus a sigma v from here minus 1 minus a sigma h, okay, so which comes from here. So, this is minus, so this will become plus 1. So, 1 minus a into sigma h. Now, we have delta u, what is the change in pore water pressure, which is equal to final minus initial. So, uf is equal to ui plus delta u. So, we are interested to find out what is that particular pore water pressure after sampling, that is nothing but uf, which is equal to what was existing in the beginning plus delta u. So, uf is equal to ui minus a into sigma v minus 1 minus a sigma h. So, this is what we get for uf when you substitute delta u, that is the change in pore water pressure. Now, let us say that the given soil element is a typical NC soil. So, A will be positive and close to 0.5. So, what is the implication? A is positive and it is close to 0.5, which means that this portion will be positive, that means ui minus some quantity, it is always ui minus some quantity. So, when it is ui is minus some quantity, we know that the final pore water pressure will be always less than the initial pore water pressure. So, it is apparent that final pore water pressure will be less than initial pore water pressure only under the condition when A is positive. Okay. Now, this can impart a negative pore water pressure because the pressure or the confinement is getting released. So, the tendency of the soil is to suck more water, and that is during volume change condition, but that is during drain condition. But since the time is less here is that we can consider this to be a typical undrained condition. If that is the case, then the pore water pressure tends to negative or suction. So, this induces a kind of apparent cohesion in the soil. This results in an internal effective stress which is instrumental in holding the soil structure together without collapsing. So, this apparent cohesion as a result of this negative pore pressure helps to hold the soil and it will not collapse and fall. So, when normally consolidated soil is sampled, it becomes lightly over consolidated because of this release, and that is the reason why it can stand on its own. Okay, so that is all about the effect of sampling. So, what happens due to release, there will be a kind of a negative pore pressure which helps to hold the soil intact. So, that is why when the undisturbed sample is taken from the field, it can stand on its own. That is basically because of the effect of pore pressure changes. So, let us summarize this lecture. Pore pressure equation is derived for plane strain condition. If the soil behaves elastically, A is equal to half for plane strain as against A equal to 1 by 3 in triaxial condition, which we have seen. Henkel'S pore pressure equation is in terms of octahedral stresses. The relationship between Henkel'S pore pressure parameter alpha and Skempton's pore pressure parameter A for constant confining pressure has been derived. A saturated soil sample from the field undergoes pore pressure changes and we have estimated it. The final pore pressure after sampling has been derived. For a typical saturated NC soil, sampling causes release of confinement. So, release of confinement induces negative pore pressure that holds the sampled soil without collapse. So, these are all the things which we have seen as part of pore pressure estimation. So, in the next lecture we will just work out one small problem just to give us a feel of how pore pressure is determined and how practically it is significant. Okay. So, that is all for now. Thank you.